Okay, properties of functions. Here's a graph of y equals x squared. It's a U-shaped graph called a parabola. I'm not sure if I've asked you in previous class, so I'll ask now. Have you ever seen a shape like this? A U-shaped graph like this? Or U-shaped like this? You have, but do you know where? Anyone?
In algebra,
Well, I mean, in so-called real life.
uh, roller coaster.
Basket,
Bat?
bowl.
Okay, that's not bad. Those aren't bad.
A boat
A boat.
on the edge.
Upside down bell.
I love these answers. The answers that come to my mind are the cable on a suspension bridge. It tends to go towards
Oh, that was my second guess.
well, okay. Another place you'll see them is in a flashlight. The mirror has a parabolic cross section. That's because a parabola is a special point called the focus. If you set a light there, then they'll bounce off the mirror and form parallel beams of light. And also, running it backwards, if there are parallel beams of light, they bounce off and collect at the focus. And that's why radio telescopes and radio antennas have a parabolic cross section. And there's one more. In the before times, I would demonstrate it, when we all met in person, I would demonstrate it by throwing something across the room. And so I'd say, hey, look, you see how it made the thing in the free fall made a U-shaped curve? Another parabola, an upside down parabola, but still. Okay, given a parabola, y equals x squared. It's symmetrical left for right. If x by x squared is on the graph, the negative x by x squared is also on the graph. That's because negative x square that is the same as x squared. So it's symmetrical, reflecting through the y-axis. Here's a graph of x equals y squared. It's a sideways parabola. And it's symmetrical up or down. If y squared by y is on the graph, then y squared by negative y is also on the graph. So it's symmetrical when you flip through the x-axis. And here's a graph of x squared plus y squared equals 1. This is the graph of a circle with radius 1 and centered on the origin. If x by y is on the graph, then negative x by negative y is on the graph. So basically, if you rotate it 180 degrees around, you get the same graph. So it's symmetrical around the origin. Now, this thing about symmetrical left for right is related to something called called parity. They're what are called even functions and odd functions. It's this is about what happens when you take f of negative x. An odd function is the one for which f of negative x is negative f of x. So to speak, the negative comes outside, it transmits. For example, x cubed is odd. We take negative x and cube that. That's the same thing as x cubed is the opposite of x cubed. Or x to the fifth, same deal. Or x to the seventh, same deal. Or x to any odd number. A graph of an odd function would look something like this. If x by y is on the graph, then negative x by negative y is also on the graph. So again, if you rotate it around 180 degrees, you get the same graph. An even function is where f of negative x equals f of x. I say it absorbs the minus, whereas this transmits the minus. So x squared, for example, the opposite of x, square that, is the same thing as x squared. X to the fourth, x to the sixth, or x to an even power. We take minus x to an even power, the negative cancels, and you just get x to the even. So if x by y, if this is a graph of a even function, and x by y is on the graph, then minus x by y is also on the graph. So it's the same as if you flipped left for right, symmetrical across the y-axis. Another question, property of function, is whether or not they are increasing or decreasing.
Excuse me, isn't that last one an even function?
Yes, these are even functions. Did I misspeak?
I was just confused there. It says odd functions in the note are left to right symmetric.
For God's sake, you're absolutely right, and I must change this. 1, 4, 2. Thank you.
Thank you.
Even function. And since you caught me fair and square, I'm honor bound to commit Hornikiri. Thank you.
I love that thing.
Oh boy. Gives you a reason to pay attention. Anyhow, absolutely right. That's great. Okay, great. Where did I put this? Page 2. Yeah, okay. This must be dealt with. Okay, now, thank you. That's a good one. Increasing or decreasing functions. I'm not a real fan of that name, increasing or decreasing, actually. Here's the way it looks. Yeah, okay. Here, an increasing function means that if you increase the input, you also increase the output. A less than B means that f of A is less than f of B. I actually prefer to think of this as order preserving. Less than turns into less than. A decreasing function goes from upper left to lower right. When you increase the input, you decrease the output. So I prefer to think of these as order reversing. But still, you can see increasing goes like this, decreasing goes like that. Some functions increase, then decrease, then increase again. This function is increasing for x from negative pi to negative pi halves, and also from pi halves to pi. Is decreasing from minus pi halves to pi halves. Now, if a function is increasing and then is decreasing, for at least a moment there, it's as big as it's going to be, at least in its neighborhood. Here it's decreasing, pause, and increasing. So here, it's the lowest it can be in its neighborhood. These are called extreme values. A local minimum is where f reaches the smallest value in its neighborhood. So here, y equals f of x. Here it reaches a bottom at a by f of a. So minimum value of y equals f of a at x equals a. A local maximum is where it reaches the largest value in its neighborhood. So here it increases the a by f of a and then decreases afterwards. So the maximum value of y equals f of a at x equals a. And by the way, and when they ask for where extreme values are, I prefer you ask all this. If it's minimum and maximum, the minimum and maximum value, and the value of x that reaches that
What is a neighborhood?
value. Nearby,
Oh, okay. I see.
sufficiently nearby. Now there's global minimum and global maximum. A global minimum is the smallest it ever reaches. A global maximum is the largest it ever reaches. So for example, here's a function, it comes from 0 up to here. Here's a global maximum. Then it comes down to here. It's a local minimum because this is smaller. It rises again to a local maximum, local because this is bigger, then down to a global minimum, and back to 0. There's a, how many ever heard of the philosopher Leibniz? Okay, fine. He said he was he was a philosophical optimist, meaning not that he's had a cheery attitude, though I suspect he did, but rather that he believed that this is the best of all possible worlds. Because why would God make a world less than the best possible? Now, the alternate philosophers love to argue, Voltaire made fun of that. He wrote a whole book called Candide, where Professor Pangloss states Leibnizian optimism. This is the best of all possible worlds. But he and Candide and the others in the troupe go through these hideous disasters. And this is Voltaire's way of saying, this is the best God could do. Give me a break. So, now, I'm surprised that Leibniz put it in those terms because he helped to invent the calculus, and he knew the difference between a local maximum and a global maximum. So I'm surprised he didn't say this is the best of all sufficiently similar possible worlds. So for example, Voltaire made fun of Leibniz for the Lisbon earthquake, a hideous disaster, and this is the best of all possible worlds. Well, I'd reply that of all the possible worlds in which there was an earthquake in Lisbon, this is the pick of the litter. And the funny part is that the concept of local optimization is central to physics and chemistry and biology. So so local optimism is literally true. Of course, if this is merely the best of all sufficiently similar possible worlds, maybe there are other worlds elsewhere. But to get to that, you first have to go down and then you have to bottom out. All right, now here we go. Here's some examples. What's the symmetry of this group, graph? Well, it's symmetrical around the y-axis. This is not the graph of a function, but what is its symmetry? Well, if you flip it around 180 degrees, same graph, so it's symmetrical around the origin. Here we have the function absolute value of 2x. What symmetry does its graph have? Well, if f of x equals 2x, then let's look at f of negative x. That's the absolute value of twice negative x. The absolute value cancels out the negative sign, so you get absolute value of 2x, and these are equal. So f of x equals f of negative x, and therefore this is an even function. What is the symmetry of the graph of xy equals 12? Well, if you replace x by negative x and y by negative y, then you get negative x times negative y equals 12. But the negatives cancel and you get xy equals 12, the same equation. So if you replace x by negative x and y by negative y, you get the same graph. So this is symmetrical around the origin. You can write that as y equals 12 over x, and that's easy to see is an odd function. 12 over negative x is negative 12 over x. So the same equation, symmetrical around the origin. Here we have a function, 3x minus 3x cubed plus 2x. Is it even? Is it odd? Or is it neither? Okay, 3x cubed plus 2x. You write f of negative x, plug in a negative x here and here. The negative comes out of the cube because cubing is an odd function. So you get minus 3 times negative x cubed. Here a negative comes out, minus 2x. And okay, after a cancellation, get 3x cubed minus 2x. But that's the opposite of this, opposite of minus 3x cubed plus 2x. So it's the opposite of f of x. F of negative x equals minus f of x. So f is an odd function. Its graph will be symmetrical around the origin. Here we have x minus absolute value of x, even, odd, or neither. All right, f of x equals x minus absolute value of x. So f of negative x is negative x minus absolute value of negative x. Absolute value cancels out the negative here, minus comes here. Now, this is not the same as f of x, so this is not an even function. Now let's look at negative f of x. Well, it would be the opposite of x minus absolute value of x, which is minus x plus absolute value of x. Again, not the same as this. So it's not an odd function either. And so therefore, yeah, okay, fine. My apologies. These aren't equal and these aren't equal. So it's neither even nor odd. Now here's a general question. Given any function whatsoever, f of x, take the function e of x, composed of equals f of x plus f of negative x over 2, the average of f of x and f of negative x. Prove that it's even. Well, simple enough. This is e of x and e of negative x. Put a negative x here and here. So f of negative x plus f of minus f of that, f of minus negative x, that equals 2. Here the negatives cancel, so you get f of minus x plus f of x, that divided by 2. But that is the same as e of x. So e is an even function. Oh, and in the book, they replace this plus with a minus and ask you to prove that that is an odd function. Well, you prove it pretty much the same way you prove this is even. Here we have a graph, and where for which intervals is it increasing? Where is it decreasing? Find local minimum, local maximum, global maximum, global minimum. All right. It's increasing for these values of x's, negative infinity to negative 4. It's increasing for these values of x from minus 0.5 to 3. And it's increasing for these values of x from x equals 5 onwards, 5 to infinity. Is this decreasing on this part of the graph where x equals between -4 and -0.5? It's also decreasing on this part of the graph where x is between 3 and 5, like this and this. The local minimum, well, is here. Local minimum is -1 at x equals 5. The local maximum is here. Y equals 1, local maximum y equals 1 at x equals 3. The global minimum is here. The global minimum is -3 at x equals -1.5, 0.5. The global maximum is here, where y equals global maximum y equals 4 at x equals -4. Oh, what do you know? I think we're done with this. Okay, stop it.